Hello everyone, let's continue with the resistive mode of operation of the MOSFET. In the previous videos or in the previous lectures we learned about the cutoff region of operation. So there are basically three modes of operation. One is the cutoff region of operation, one is the resistive operation, and there would be one more which is saturation operation. So we'll be looking into all of them. So the second region of operation is the linear region or the region of operation. So let's try to look into that, and let's try to look into every detail bit of it. So for example, this is where we had stopped in the cutoff region. So the gate to source voltage at which this strong inversion happens, it's referred to as threshold voltage, and your semiconductor surface inverts into completely into an n-type material. So over a p-type substrate you have an n-type material, and that's when it's called a strong inversion. So the voltage at which that happens, it's referred to as threshold voltage. Okay, so that's where we had stopped in the previous videos. Next is we have to see what happens now, since we know that at VGS equal to VT we have some phenomena that's happening. Now we have to observe what happens at different voltages when we increase VGS greater than VT. So one thing is very obvious: the way you increase the VGS, that there will be more and more charge carriers in the channel region, and you will find more and more conducting area between the source and the drain. Okay, so for example, let's observe this region. This is if this was the area, if this was the channel width, while you increase your VT to, let's say, just equal to VT, when you increase your VGS equal to 1 volts, your channel width increases. Just observe over here how the channel width increases. Now if you increase your VGS to 1.5, your channel width increases even more. Now if you increase your VGS to 2 volts, your channel width increases more. So what does this say? It basically says that the induced charges, because of the gate voltage, it's proportional to the gate voltage. So the charges that gets applied or that gets induced or that gets accumulated in this area, that is proportional to VGS minus VT. So any voltage which is greater than VT, so VGS minus VT is basically the potential which is needed to turn on the transistor. Okay, so VGS will only VGS equal to VT will be creating the strong inversion, and anything which is more than VT, which will be called as VGS minus VT, and that amount of voltage will create an equivalent amount of induced charge in the channel. So that's what it means. But if you ask in reality, that's not close enough. So we have to look into looping all the loops over here, into closing all the loops over here. So for example, now what we'll do, we'll apply a small drain to source voltage. So for example, let's start with, we'll start with some assumptions. Okay, so let's analyze this same circuitry at VGS equal to 1 volts. So VGS equal to 1 volts is good enough to create an induced charge, or to create a short circuit channel between the source and the drain, or a conducting channel between source and the drain. Okay, so let's analyze it at VGS equal to 1 volts, and let's say VDS is equal to very small, which is 0.05 volts, 50 millivolts. In that we'll start from that voltage, and then eventually we'll be moving into higher voltage of VDS. But to start with, we'll start with VDS equal to 0.05 volts. Okay, it's very small enough. So so let me explain you a few things over here early itself. So VDS, whenever it's less than VGS minus VT, things behave differently, and whenever you have VDS greater than VGS minus VT, things behave a bit separately. So we'll talk about this behavior in some time from now. For example, right now let the VDS be very small, 50 millivolts, 0.05 volts, and let the VT of the, assume that the NMOS for the VT for this NMOS is 450 millivolts or 0.45 volts. Okay, let's put it down over here. So you have VGS equal to 1 volts, you have VDS equal to 0.05 volts, and you have VT equal to 0.45 volts. Okay, so one thing is very clear: since VGS is greater than VT, this transistor is turned on. You have a conducting channel between the source and the drain. Now with the application of small potential at the drain, we'll see what can happen over here. Okay, so let us try to do some quick assumptions over here, and they're not really assumptions, they are realistic things, but we'll just put it in this transistor. So we have been looking transistor from a schematic point of view. Let's try to look the transistor into a bit detail from a physics point of view. So how does physics looks into transistors? So now in this case, you have your source which is connected to ground, you have your drain which is connected to VDS. So ideally, if you see, if this point of your channel it's basically close to source, and this will be at zero potential. Okay, this point of the channel which is close to your drain will be at VDS potential. So there will be a voltage gradient over here. The voltage is not constant all over the channel, but there is a voltage gradient, so it starts from 0 and ends at VDS. So let's plot it over here. So we will have two plots, we'll have 2 points. One point will be at VDS volts. So this point is at VDS volts because it's close to drain, and we just applied a small potential of 50 millivolts at drain. So this point is as VDS, and this point is at 0 because this is close to source. Okay, close to the source terminal. So there, if you see, there is a voltage gradient over here, so the voltage is not constant across the channel, and that's a very important discovery is over here, or an observation over here, that the voltage is not constant. In the absence of VDS, it was constant. When this was connected to ground, the voltage across the complete channel was constant, but now it's not. Just when you apply the drain to source voltage, the voltage is not constant. Okay, so let's try to tune some equations over here. So this thing is true in the absence of VDS, but once you have the VDS in place, we have to fine tune these equations to get the correct ones. So let's do that. Okay, so if you have this effective channel length as L, so the difference between the channel length and effective channel length is the one that you see after process. So for example, the channel length was expected to be, let's say 100 nanometers for example, but the effective channel length will be much less than 100 nanometers. These are all because of the fabrication techniques, and we'll be talking about how does the fabrication techniques actually reduces the effective length. Okay, so because of the fabrication techniques, the effective channel length is much less than the actual channel length, and for now let's assume that the effective channel length is L. Okay, so now since the effective channel length is N, let's try to go into even deeper into this device. So let's plot a graph. So this is your x-axis. Okay, this is your y-axis. So x-axis basically represents the channel length. So you go from 0 to L, so that's basically your channel length. Okay, and y-axis basically represents your width. Okay, so V of x, if you calculate the voltage at across the x, V of x will be the voltage at every point of x across the channel. So for example, let's say we'll take some values of x. Let's say x is 0, x is 1, 2, 3, 4, and finally x is L. So at every point, V of 1, V of 2, V of 3, and V of L, at every point the voltage will be different. And let's try to give a value to it. And let's try to say that V of X is the voltage at any point on this particular channel. Okay, so at this point, let's say let's say this is L by 2. So the potential at this point will be V of L by 2. The potential at this point will be V of 0, let's say, and the potential at this point will be V of L, and all will be different. And why they are different? Because of this small voltage that we have applied. It won't be very much different, but there will be some difference in the voltage across the channel, just when you applied the drain to source voltage over here. Okay, so now your total voltage, so for example, you had applied VGS. In the absence of VDS, every point on the channel had got VGS voltage, but with the application of VDS, every point on the channel will have a voltage of VGS minus Vx. Why so? Because V of X at this point is 0, V of X at this point is VDS, and V of X at every point lies somewhere between 0 and VDS. Okay, so your effective channel voltage or gate to channel voltage on the application of VGS will be VGS minus V of X. So at every point the voltage will vary, and this is a very important point to understand, because that will actually that will eventually lead to the current flows, and the current flow equation will vary based on what we learn in some time from now. Okay, so what we'll do is we'll go a bit slow. We need some more minutes and time to discuss this part, to discuss the actual current values at each and every point, or basically the current that flows from source to drain. We need some more time. We will be deriving some equations, and these are the equations that you will be using overall for all your simulations and for all your circuit design. So that equations, or that drain current equations, is the one that will be driving complete delay of your cell. So I'll show you how do the delay of the cell is actually driven by the drain current equations of the cell. So let's try to go slow. Let's try to stop at this point, and we'll continue in deriving the drain current equation at the resistive operation region of transistor from the next video. Thank you.